In this video, we explore image-coupled volume propagation for stereo matching, introducing a novel neural network model to densely estimate disparity maps, ultimately achieving accurate and efficient depth estimation. Our primary goal is to achieve a comprehensive 3D model of plants. However, this task is challenging due to thin leaves and the self-occluding structure of plants. Robust depth estimation is crucial for fast and robust 3D plant reconstruction. Unfortunately, existing low-cost RGBD sensors have limitations. Stereo-based sensors lack accuracy, and LiDAR scanners, being inherently slower, can introduce motion artifacts. Structured light sensors also struggle in bright sunlight. Even commercial RGBD cameras, proficient in various scenarios, face challenges when it comes to 3D plant reconstruction. An effective approach for obtaining accurate depth information is stereo matching. Stereo matching is the process of accurately estimating dense disparity maps, which reveal depth information, from the left and right images. It's a critical component of computer vision systems used in various industries, including depth cameras, robotics, 3D reconstruction, and more. Although the mathematical principle for depth from stereo is clear and old, solving the pixel matching problem remains a challenge, especially due to occlusions between image pairs, matching ambiguity in featureless areas, and thin geometrical structures. A widely adopted general architecture in stereo matching consists of 4 key building blocks: feature extraction, cost-volume construction, cost aggregation, and disparity regression. In feature extraction, both left and right images pass through 2D convolution layers with shared weights to create feature maps. Next, the initial 4D cost volume is constructed, where each voxel is determined by applying methods such as correlation, concatenation, or group-wise correlation to the corresponding pixels from the left and right feature maps. Cost aggregation refines the constructed 4D cost volume through 3D convolutional layers, enhancing the scene's geometric understanding. Finally, disparities are computed from the refined 4D cost volume, typically by using the soft argmax operation. While 3D convolution layers are effective for refining the 4D cost volume, they also present challenges. First, they consume substantial memory due to the large 4D cost volumes, which also places significant demands on computing resources. Moreover, 3D convolution layers may cause the loss of fine details in the scene, attributed to their inherent smoothing power. The core idea of our approach is to utilize the left image, which contains crucial cues for capturing thin geometry details. Please note that depth estimation from a monocular camera is already a widely researched area. Additionally, processing a single image feature map is significantly less resource-consuming than handling 4D cost volumes. In our approach, the model tightly integrates feature maps from the left image into the cost aggregation stage. By doing so, it alleviates workload on 4D cost volumes and improves the reconstruction accuracy of fine details. Our approach follows a general framework composed of 4 key building blocks: feature extraction, cost-volume construction, cost aggregation, and disparity regression. Our feature extractor employs a U-net structure to produce feature maps from each left and right image, and the cost volume is constructed through group-wise correlation. Following our novel cost aggregation module, the final disparity is achieved by applying the soft argmax operation to the refined cost volume. The contribution of our approach is on the cost aggregation module that achieves a symbiotic relationship by coupling image-based depth cues and shape completion with established 3D convolutions of the cost volume. The model is equipped with 2 parallel U-net structures with unidirectional connections. In the 2D propagation part, image-based cues traverse through the 2D U-net network. In parallel, the 3D propagation part convolves the 4D cost volume while incorporating the feature maps from the 2D propagation, resulting in the jointly evolved 4D cost volume. Both the 2D and 3D propagation parts in our model consist of encoder and decoder layers. The encoder processes input data, gradually reducing resolution while capturing higher-level contextual features. In contrast, the decoder's role is to restore the original resolution while integrating data from skip connections and higher-level contextual features from deeper layers. While the 2D propagation forms a typical 2D U-net network, the 3D propagation incorporates additional fusion modules that receive inputs from both the 2D and 3D propagation. In these fusion modules, Each input from the 2D and 3D propagation passes through an address convolution layer, and they are fused by broadcasting sum. Here is why the simple broadcasting sum is sufficient to successfully integrate image features into the cost volume. You can imagine the most straightforward way to incorporate the feature map into the cost volume is to concatenate the feature maps at each slice plane of the cost volume along the disparity dimension. In this case, a voxel of the cost volume will embed a vector of the geometric context from the 3D propagation and the image feature from the 2D propagation. However, when 3D convolution is applied to the concatenated cost volume, the operation is equivalent to the broadcasting sum of the feature map and the cost volume, both of which were processed by individual 2D and 3D convolutions before. This approach results in considerably less computation and GPU memory consumption. With the efficient fusion module, our model is able to seamlessly couple the left image feature into the cost volume throughout the propagation with a low impact on computational resources. Here is the visual comparison with other state-of-the-art methods on KITTI 2012, ETH3D, Middlebury benchmarks. As for the quantitative results, our model achieves the second position on KITTI 2012 benchmarks for 3 all, 4 NOC, and 4 all metrics, as well as on ETH3D benchmarks for BAD 2.0 and BAD 4.0 metrics. Notably, our model exhibits significantly faster runtime than methods with comparable scores. Our model is capable of efficiently generating high-resolution depth maps from a stereo pair of full HD images with a maximum disparity of 400, leveraging the capabilities of recent commercial GPUs. With our research, we hope to improve the acquisition of 3D plant models in practice. Thank you for your attention.